Another speaker, Jiang from Beijing University of Chemical Technology. So he will talk about spin cargo mole systems and their superintegrability. So now, Kai, you may start your talk.
Okay. First, thanks for the invitation and the introduction. And today, I'll talk about the spin collector model system. Gary just talked about collector model system. So let's continue for this system and generalize it to the spin case. Okay. And this is the outline of the talk. First, about collector model system, classical one and the spin one. And then we'll talk about its superintegrability, and the last part is the SU3 case, because we can understand the superintegrability by the concrete computation. And the first one, what is the Calogero model system? It is a system of n-point particles of equal mass m, and moving on a line on the interaction pairwise can be described as a Hamiltonian of the form like this. Okay, first part, this is H is a Hamiltonian, and the first part is the energy, and the second part is the potential. So the energy is quite clear. Yes, it is pi are the momenta, so it's square. Okay, the energy part. The second part is the potential part, and Qi, Qg are positions. So what is V? V here, it is a potential function having second order pull at the origin. So usually it is, for example, Qi minus Qg square. 1 over this one. 1 over Qi minus Qg square. Okay. So it depends on the on this V. For mathematics, usually we can make this the mass m to be 1, and the g, the coupling constant, is equals to 1. So we can consider this, we can simplify this Hamiltonian in mathematics. Okay. So there are different kinds of types of Calogero systems corresponding to this V, the potential function. So let's see what is. There are basically there are four types of c- uh, uh, Calogero systems. We call it a rational one, parabolic one, trigonometric one, and the elliptic case. Okay, what is when the simplest one, the second pole of the potential function, it looks like this. See, if V is like this, okay, it is that's the easiest one. We call it a rational case. And the hyperbolic case, in the denominator divisor or the divisor, it is the hyperbolic sine square. Okay. A here, it is a constant. You can consider it as a 1. Okay, and the trigonometric case, we also call it Calogero-Sutherland or Calogero-Moser-Sutherland system. Here, the divisor here, denominator here, is sine square. Okay. And for the elliptic case, it's the most complicated. It is related to the algebraic geometry, and we have the Weierstrass row function here, and it's quite complicated, but this is not the topic today. And one remark is this: the elliptic case can be reduced to the first three cases. It means that if the one, two, three, four. The first one is the simplest one. The second and the third, they are equivalent, because if we make a signs here as the pure complex one, we can exchange one to the other. The fourth one, the last one is it is the most general one. Okay. Today we will talk about the third one. We call it Calogero-Moser-Sutherland system. What is the difference? You can see that from the definition, the n particles moving on a line. Okay, but the trigonometric one, it is sine, so it is periodic. You see, it is as we know that the function trigonometric functions are periodic. So here we can consider it on a one-dimensional manifold, it is a circle. We can consider that n particles they move on a circle. So if they for example they rotate, after the rotation they can be if we identify all we do not distinct the particles, they can be periodic on a circle. Okay. So, what is same system can be also realized by Hamiltonian reductions as the following, just as Gary just Gary's talk. Let G be a simple Lie group, and this small g is this Lie algebra. And consider the action of G on the cotangent space like this. The cotangent space can be written by the right or left trivialization. And this is the conjugation. Yeah, this is the standard conjugation. This action is Hamiltonian, and the moment map is also standard. We can compute it by definition directly, and this is the J. We denote it by J, the Hamiltonian. So this J is we map this X in the dual of the Lie algebra and gamma to this one X minus gamma gamma inverse X gamma. All this moment map is standard. So okay, the point is if we pick an element in the dual of the Lie algebra and let OC be the co-adjoint orbit in G star, okay, then we can the reduced space is like this. It's a quotient space like this. SC here, SC is defined as the pre-image of this co-adjoint orbit quotient by this G. Okay. Of course, this is if we use the standard Hamiltonian reduction, we can see that okay, it's the inverse of this element quotient by its stabilizer. Here is the isotropic group or the stabilizer group. Okay. So after this, we can consider the trace space trace function hx x gamma defined by the trace of x squared on this cotangent its cotangent bundle trivialized by left or right trivialization. Okay, we can by concrete computation, we can see that this definition, this trace, this one is exactly what we have at the beginning, this one. Okay, if we write this x, this computed, if this one can be directly computed as the same as the Hamiltonian we defined before, and we can use the lax pair and something like that to show that this trace function is exactly the same. Okay, it is invariant. Under the diagonal co-adjoint action by G. So the moment map G is G equivalent. So this H is defined under cotangent bundle, but it can be regarded as a G invariant function. So it can be regarded as a function on the reduced space, this reduced space, because this G is the G equivalent, and yes, and the trace function is invariant. The two conditions. It's invariant and the G equivalent. Moment map is G equivalent. So this H can be reduced in the quotient space, our phase space. Okay. Now, particularly if G equals to SUN or SLN, this is the real form of the SLN. Yes. This is the complex one. This is the compact Lie group. Yes. So, and particularly, and I see, we choose a special orbit. This orbit passes through this particular point. Okay, and we call it this is a rank 1 case, and if we in this particular case we can get exactly the classic Calogero-Moser system. Then in this case, this trace is exactly what we defined before. And this we can also define its the functions commuting with this Hamiltonian function like this HK. HK is defined as the trace of X in the power K. So then we can verify directly that this H1, H2, H3 till Hn, they compute pairwise. So we in the classic so this is why the classic Calogero-Moser system is Liouville integrable. We can find the we can find n minus one functions which commute with the Hamiltonian. So we can do it by construction, direct construction. But what is the spin Calogero model? The spin Calogero model, it is we should introduce the spin variables. Before here, we use, for example, in the rational one, in the rational spin Calogero model, it is looks like this. Before here, it is one or a constant. This part we can go back. Yes, here. Here we can see that for the rational one, this is a constant one or c as you it's just a constant. But for the spin Calogero-Moser system, we should introduce the spin variables. And here P, Q are still the momenta and the positions. And another way to think about the spin Calogero-Moser, it is the rank. We do not choose the rank 1 orbit. Before we choose this particular orbit, OC, passing through CCCC, the diagonal CCCC minus n minus 1c. So if we choose other point and the orbit is with rank bigger than 1, for example, the rank 2, 3, 4, as you like, we call it spin Calogero-Moser. So we should, but in this case, we cannot say that, oh, this still Liouville integrable. It is not possible because you see, we can prove that we can still define this trace function as H2, H3, H4 till Hn, but we still have n minus one functions which are independent and they commute pairwise. But you see that the phase space is grows bigger. The dimension is bigger because we have more variables. We call it spin variables. So it is no longer Liouville integrable. So we should introduce the superintegrable. It means we do not have enough. We still have the first integrals or the integral of motions, but they do not commute pairwise anymore. So let's see the definition. What is this? What is the superintegrability? We have several viewpoints to see it. First one is the classical one. The classical one is just like the Liouville integrability. It's just like to see that yes, we have several for example, in the 2n dimensional manifold, symplectic manifold, M2n, and we have an integer k. K is smaller than n, smaller or equal to n. Okay, and H2 till H2n minus k. So we have less than n, functions. So here we have, oh, sorry, we have here it is more first integral or the integral of motions, but we require that their first k functions they commute pairwise. The first k, but the first k, the one from the first k and the one from the last 2n minus 2k, they do not commute. They may not commute. And of course, we require that all the functions are functionally independent. In this case, we see that we still have first integrals or integral of motions, but they do not compute pairwise, but only first part of some part of them commute pairwise. This is the superintegrability. Okay. From the definition, we can use the language of algebraic approach. For example, we see that, okay, what is a superintegrable system? It is uh, we have a symplectic manifold M2N. It consists of a Poisson algebra A, okay, of rank 2n minus k. Okay, we can consider as before, it is generated by the H1, H2, H3 till H2n minus k. Okay, there's an Poisson algebra A of rank 2n minus k. And and we still have its Poisson center, Z8. This Z8 is of rank k. This is rank k. What is this? Its center? Its center is just generated by its first key functions of this algebra. Okay, we can compare the two definitions. Okay, so this is the algebraic approach. And still we have the geometric approach. Okay, in someone we can, generally speaking, we can consider that, okay, this is the M2N. Okay, we leave it here, but we consider that we take the spect of this algebra and spect of its center, also an algebra. So we can get this one, M2N, it's still there. And here P is a Poisson manifold. It's a Poisson manifold. Here, D is also a Poisson manifold, but with a trivial Poisson because every function in it on it is every two each pair of functions they commute. So here is Poisson. We just require that this psi and pi is just Poisson map and the surjective. Okay. So if we have a manifold M2N and a Poisson manifold P and a trivial Poisson manifold PK and the two Poisson submersion, okay, surjection of psi and pi, then we get also a Poisson a superintegrable system. Okay, this is the equivalent definition. Okay, we still have this superintegrability. We have the similar result of Arnold-Liouville theorem. It says like this: the first part is still the simpler as the action undergo coordinate. This theta is the periodic one, so this angle coordinate. This H action coordinate, and this omega. This omega is the last part, is the third part. It's still a symplectic manifold. We just know that it's a symplectic manifold. We do not know more about it. Okay, this is quite similar to the classical Arnold-Liouville theorem. Okay, in 2003, Nicola Rosikin proved that the spin Calogero-Moser system are superintegrable. Generically, it means that if we choose a generic orbit, okay, it is good, and we can construct exactly this three manifold. The first one is symplectic manifold. The second and the third one, the second one is a Poisson manifold with this trivial Poisson manifold. Okay. Okay, the proof is standard just a construction. We use the normal form or something. Yeah, we just construct the size, the pi, and the PB. Okay, we can write it explicitly. So following there's a problem is in generically here generically means that this after this quotient we get a manifold, but in general the quotient space is not a smooth manifold. It may be a stratified space. A stratified space, especially for example, when this action is not free, it's not proper, we cannot get a manifold. So here we should get a stratified space. A stratified space is just like you can consider this as a disjoint union of different structures with different dimensions. And each dimension will have a frontier condition. It means that if one strata and of another strata, the interaction is not empty, we have this one. We have that M alpha should be contained in the closure of M data. Okay, we have this order. So we have this. This is you can consider that as a manifold with boundary. Then the boundary is a lower dimensional strata. Okay. So what if this phase space is no longer this phase space is no longer a smooth manifold, but a stratified space? In fact, we have a Lerman-Schmalz theorem or famous theorem proved in 1990 by Schmalz and Lerman. They say that, okay, although the space is not a smooth manifold, but on each strata is still a symplectic manifold. Okay, so we would like to show that, okay, so what we would like to show, yeah, this is a stratified space. We still have a stratified space and still a stratified space. And although the stratified space are quite complicated, but we can still find a open dense subset on each strata, on each stratum, such that the stratum still have the superintegrability. So in general, we can see that, okay, this is a diagram to illustrate the stratified simplicity space. Okay, you see here, it's maybe the arrows goes to everywhere. But we would like to see that, okay, this is a definition to show to see what is superintegrability in stratified space. Here we should see, okay, this definition is complicated, but this diagram, this illustration is clear. Although we have this C pi, the arrows is quite complicated, but we can always find a open dense an open dense subset on each stratum. For example, here we use this O to denote the open dense subset of this M alpha. So if there exists for each stratum, there exists an open dense subset such that, okay, on this subset, the arrows are quite simple. It means that, okay, there's only one arrow from one space to another space. There is like this. So this is the key point. The most important part is this. Although if we consider the the maps is quite complicated, but there is always exist a main part, an open dense subset, such that the arrows is simple. And on each arrow, okay, for each arrow, each chain, it is a manifold. It is a chain between among manifolds. So we can use the classical superintegrability. So, and last, we see that this is our main theorem. Still, for the spin Calogero-Moser system, it means here G equals to the special unitary matrix and obtained from Hamiltonian matrix, from Hamiltonian reduction. And the superintegrability still holds. It still holds. It means that, okay, okay, as I do not have more time, maybe 1 minute, I will use an example to show the result. Okay, here, if in SU3, this is a special case. This is in SU3, we choose a special orbit or a special point. This is A0 minus A. This is our orbit passing, yeah, on which this is the orbit passing through this C. So we have this stratum, we have two stratum on the phase space. And in the middle, we construct two space, Poisson space. And here, the last space is just one space. Okay, it's just one manifold. There's no just one stratum. So we can find an open dense subset on this six dimensional space to this 4-dimensional middle space, the Poisson space, to this 2-dimensional base space. And this one, the lower dimensional space is 4-dimensional space of the phase space and the 2-dimensional space in the middle, and it goes to the base space. So we still have this superintegrability. In this chain, and also in this chain, this one goes to P2 and it goes back to the base space. So we see that, okay, now not for generic orbit, but for all orbits, we can find the superintegrability even if the phase space is not a manifold, but a stratified space. Okay, this is our main result. Thanks for your attention.
Okay, okay. Let's thanks Kai